ब्लॉक
They announced it that you will have a tutorial on Monday. On Friday, please select whichever day is convenient and then you stick to that. Only 2 days you will have the tutorial. Monday, Tuesday and Friday, you will have a tutorial. Obviously, they will have the tutorials are made in the time. So most of the applications those were pending with me for the lab pressure and others, I have already cleared. There could be some students those who are joining for the first time today. So for them, again we will go through the course strategy and then we will start. So the main important point to note down here is the attendance is compulsory. Your attendance should be more than equal to 75%, otherwise you are going to get 0 marks. Okay. If you attend more than equal to 75% classes and tutorial, then you are going to get 10 marks, otherwise 0. Then there are 3 examinations, 1 minor and 2 quizzes. Out of 3 examinations, you have a choice of between 1. There is only quiz, there is only minor. And all 3 examinations will be same. So it has aimed at P1 and P2, but they will be same as finding type of question. Don't get in an odd session that will be execute type. No, it will not be execute type. It will be regular minor exam. Okay. So block 1, if you have a trouble in sitting in the front, they will sit here. That is the block. Okay. So I will come once in a while, but I usually like to roam around here. Why? Because and the last thing which I wanted to say here is major examination will be having 40% marks. All examinations including major, P1, P2, minor 1, these are going to be open. The book we are going to follow is Chemical Process Control by George Peterson. You can buy this book. I will be allowing only this book in the examination, nothing else. If you bring the Xerox copy, I am not going to allow. No Xerox copy, no class notebook, nothing will be allowed, only the hard copy of the particular book will be allowed. To buy it from the Amazon, it is around 200 rupees. Okay. If you don't want to buy it, perfectly alright, you can get it from your seniors. You get it from wherever you wanted to get, but get it. Okay. So all examinations, all regular examinations are going to be open. But if you miss the major examination and give me that certificate and ask me to do the re-major is a closed book and a published lab. Okay. So don't miss it unless it is absolutely required. Okay. Highlight the text in the book, but if you want to write it and like the definition is already there. I will reinvent the definition. So why I am saying no, because I know what type of English for right. So I have gone last how many days. That is why I am not allowed. Earlier I used to allow even the classroom and everything, but they want to give it. I have to now. The initial part will be the book. In between there will be something else. Okay. Alright. So hard copy of the book is allowed. You should not be writing anything inside, isn't it? At max you can highlight the content. Whatever I am covering in the slide is all there. Wherever I am deviating from the book, then I usually tell the class that this part is not there in the book. Alright? Okay, so in the last class we started with what is chemical plant, why control is required in the chemical plant. We said that chemical plant is very much the rational arrangement of it's made so that we can convert the raw material into a finished product by using the utilities that energy in more efficient manner. That's it. But then we said that the chemical plant usually involves the dynamic behavior. So it's not a static condition. So things are changing in the plant time to time. So whenever there is a feed into the plant, that feed input will never remain constant. It's going to change, isn't it? Also, the fluid is involved in the chemical plant. So if you are transferring fluid from one vessel to another, there is a surging of the fluid takes place. Sometimes there is a boiling is taking place, and because of that, the chemical plant is always dynamic in nature. So whenever a system is dynamic in nature, with dynamic changes coming into the plant, are these dynamic changes leading to violation of different constraints or the objective which you have in mind? So there are several constants which you need to satisfy. Different constants like you need to satisfy whether the plant is safe for the operation, whether the production specification is satisfied or not. There are several constants given by the environmental agency, pollution control board, etc. And also you wanted to make your plant profitable. So all these objectives and constraints are satisfied or not whenever there is a dynamic change occurring in the plant. So you need to find out that. So in order to find out this, you need to monitor the plant. So first step involves is monitoring the process plant. So when I am saying the monitoring of the process plant, what it means is we are measuring all the important variables that are given in the plant. And whenever these variables are deviating from their set point value, we try to bring these variables back into the given set point ranges, isn't it? By doing the external intervention. And this external intervention we are calling it as a control. So typically the process control is called primarily for three main reasons. The first reason is to suppress the effect of external disturbance on the system. The second important requirement is to make inherently unstable process stable, and the third important requirement is to optimize the process. So these are the three main requirements for which the process control is called, and we are going to look at each of these cases in detail. In the last class we started looking at the first case, suppressing the effect of external disturbance on the system. A typical example which we have seen in the last class is this, isn't it? There is a state tank system where there is the inlet flow rate Fi and the inlet feed temperature Ti, and continuously the effluent is coming out from the state tank reactor, at a temperature of T and F. Our objective is to maintain the temperature of the effluent coming out from the reactor, and also we don't want this tank to overflow or go dry. So our control objective in this case is to maintain the height of the liquid present in the tank. and also to maintain the temperature of the reactor present in the tank. Okay. And these two important control variables may change if there is a change in Fi and Pi. Okay. So whenever there is a change in Fi and Pi, even though there is a change in Fi and Pi, can I make the effect of this disturbance? Can I negate this effect of the disturbance on the control variable? This is what we are looking for. Okay. So the first system which we have studied in the last class is a feedback control system where we are trying to maintain the height of the liquid inside the tank even though there is a variation in Fi by manipulating the outlet flow rate. So you can see that whenever there is a change in the height, the change in the height is measured by using level measurement device which could be a differential pressure cell. It can measure the height of the liquid present in the tank, and if this height is deviating from the set point, in that case whatever the error we are getting, so this Hm is nothing but the measured height and this Hs is nothing but the set point value of the height. The difference between these two, Hm minus Hs minus Hm, that will give you error, and based on the value of the error this controller is going to open or close this valve. So you can see that the effect of the disturbance is first felt on the system and then you are acting based on the impact you have measured, isn't it? So in this case the control system which you are implementing is a feedback control system. Why? Because the effect of the disturbance is felt on the system. Okay. So another example which we have seen here, in this particular example also we are controlling the height of the liquid present in the tank by manipulating the inlet flow rate. And this particular system is also an example of feedback control system. Why? Because the effect of the disturbance is first measured here and then you have activated. So both these cases are feedback system, isn't it? Similar to the previous case, in this particular case we are trying to maintain the temperature inside the tank by manipulating the steam flow rate to the jacket. So in this case you can see that the temperature is measured by using thermocouple. This measured temperature is compared with the set point temperature, and whatever the error we are getting, that error is given to the controller, and controller depending on the value of the error, it is opening and closing the valve which manipulates the steam flow rate. Correct? This example is also corresponding to a feedback control system primarily because the effect of the disturbance is first felt on the system and then you are active. Isn't it? Now let's digress from this example. Let's look at another control system. In this particular system you can see that even before the disturbance is acting on the system, we have measured the disturbance itself. We have measured the disturbance itself. And whenever there is a change in this disturbance variable, then we have manipulated the steam flow rate. So you can see that even before the disturbance is acting on the system, you have already performed the control action. So you are acting on the control part even before the disturbance is acting on the system. So clearly this particular system is referred as feed-forward system. Isn't it? Again, the interesting part here is the feed-forward control system has a potential for 100% control. And a theoretical potential for 100% control. Why? Because even before it is acting on the system, you have started control action. Theoretically, it is possible to have a perfect control. Okay. Unlike this, if you look at a feedback system is always compensated. This particular control system is anticipated. You anticipate the problem and then you act. Feedback system is compensated. Whenever the system is messed up, whatever the changes are happening in the system, that you try to rectify by performing the external intervention. So it's compensated. So you can see that feedback system can never give you a perfect control. Feed-forward control system can. Isn't it? Still, even though there is an advantage with a feed-forward system, still people prefer to have a feedback system. In an actual industry, primarily because the feed-forward system requires identifying the disturbance required. Here you have identified that this Ti is the disturbance, but you can see that this Fi can also be a disturbance. In this case, I have taken a simplified case where only Ti is varying and not Fi. I could have taken both Ti and Fi, isn't it? So identifying the disturbance is required in a feed-forward control system, and that is the difficulty why people prefer to have feedback system instead of having the feed-forward system. In an actual real life industry, you usually have the number of variables which are in thousands, isn't it? Identify which variable is disturbance and which variable is not disturbance. So there you only look at how much my system messed up, and then you perform the compensatory action. Okay. So that is the advantage with respect to the feedback system compared to the feed-forward system. But whenever you know pinpointedly that this particular variable is the disturbance, then the best control system is a feed-forward. Okay. All right. Is it clear? Okay. Now let's move to the next requirement. Remember I said that the process control is called upon whenever there are three main requirements. The first requirement is to suppress the effect of disturbance on the system. That example we have already seen. Okay. The second requirement is to make inherently unstable system stable. So I am putting this another term, stability here. What is stability of the system? Anyone? When we can say that the system is unstable? Changing with time, always things are changing with time in process plan. Process plan dynamic nature. But not always we call a plant unstable.
Instead of becoming error, it's growing with time.
It's growing with time. Only if the disturbances, only if the impact of the disturbance on the system is growing with time, then you call the system unstable. So whenever there is a bounded input given to the system and that bounded input given to the system is leading to an unbounded impact, then the system is referred as unstable, isn't it? For instance, in this particular case, you can see that the bounded input is given to the system, bounded disturbance is given to the system at time t equals to 0, and because of that you can see that the output variable is also disturbing at time t equals to 0. You can see that this output variable is varying and finally this variation is dying out with time, isn't it? So my output variable, initially it started some variation, but that variation is then eliminated over the time, isn't it? So clearly this particular system is stable. But if you look at the another system, here you can see that at time t equals to 0, when I have given a disturbance, with that disturbance either this output variable is continuously increasing, or this output variable is continuously decreasing, or this output variable is increasing with increasing amplitude like this, isn't it? Then my system is unstable. Then my system is unstable. So the notion of stability is clear to everyone when we say a system is stable and when the system is unstable. When we give a bounded input to the system and the output is unbounded, then we call the system unstable. This word bounded is very, very important, isn't it? For instance, if you give a ramp input to a system, ramp input is not a bounded input. So you will not be able to say anything about the stability if the ramp input is given to the system and if you are getting the output which is unbounded, you are not able to say anything. But if you give a step input is bounded. If you give an impulse input is also bounded. If you give a sinusoidal input, that is also bounded. So you will see that later when we will look at the stability, when we try to understand more details about the stability, we give the input like step input, we give impulse input, we give sinusoidal input, but we don't give a ramp input, because ramp input is not a bounded input. When we talk about the stability, we have to give a bounded input. Okay, is it clear?
what is that?
Ramp input means it is continuous input. With time. Okay. Alright. Now, remember I said that the process control is called upon whenever there are three requirements. The first requirement is suppressing the effect of disturbance on the system, and the second requirement is to make inherently unstable process stable. The classical example is cycle. The cycle is unstable initially because it can topple this way or other way. But when you are driving, it's not toppling. Based on the patterning, based on the steering, you can drive it very well. Isn't it? So this external intervention is making your inherently unstable process stable. Is there any example in process industry similar to this? Have you seen any example in process industry where the system is inherently unstable, but you have to make it stable? You all have done reaction engineering, isn't it? So have you studied the multiplicity of the continuous sort and reactor? So you can see that whenever you look at the multiple operating points for this step type reactor, some of the operating points are inherently unstable. Yes or no? Have you seen? Not seen? Not seen. Alright. So take an example of stir tank reactor. In this particular case, you can see that the inlet is CAI, FI, TI. CI is the concentration of the reactant A. FI is the flow rate of the reactant A. And TI is the inlet temperature. So you are continuously taking the input to the reactor, and inside the reactor a reaction is occurring, A gives R. This particular reaction is exothermic, so heat is liberated in the reaction. This particular reaction is exothermic, so heat is liberated in the reaction. And this exothermic heat is removed by a coolant which is flowing through the jacket. So coolant is coming in with the flow rate of Fc and temperature of Tci, and the coolant is going out from the jacket with flow rate of Fc and temperature of Tc naught. And the temperature of the reaction mixture inside the reactor is T, and the flow rate of the effluent coming out from the reactor is there, and the concentration of reactant A inside the reactor is C. Okay. Now this is a classic example of unstable process. Why I am saying this? We will prove that. So you all have done reaction engineering. If I have to write down the model equation for CSTR, this is the model equation, isn't it? Residence time or phase time is given as Ca naught XA divided by minus RA. Minus RA here in this case is a rate of reaction, isn't it? Correct. Ca naught is the initial concentration of A, XA is the conversion. Correct. If I replace this minus RA by, in this case, A gives R, this is the first order reaction, so I can write down this minus RA as KCA, isn't it? And KCA can further be represented in terms of the converter as KCA naught 1 minus XA, isn't it? So I can replace this minus RA by KCA naught 1 minus XA, isn't it? And if I rearrange everything, the CA naught will get cancelled out. If I rearrange everything, I can represent XA. So this XA can be represented as K tau divided by 1 plus K. K is the rate constant. I can represent K in terms of the Arrhenius constant and temperature. So that can be represented as K can be represented as K naught e raised to the power minus E by RT2. Where E is the activation energy. Correct. So now in this case XA is given as K naught tau e raised to the power minus E by RT2 divided by 1 plus K naught tau e raised to the power minus E by RT2. If you look at this particular equation, this equation is coming from this mass balance equation, isn't it? So this XA which I have calculated is calculated based on the mass balance, isn't it? This XA is calculated by using the mass balance. If you look at this particular equation, what type of representation I am going to get? If I look at how XA is varying with respect to let's say temperature, how that graph will look like? Anyone? You all are JEE pass out. You should be knowing what type of curve you are expected to get. You are expected to get a sigmoidal curve, isn't it? Because this equation is a sigmoidal equation, isn't it? You are expected to get a sigmoidal curve. Now let's look at the energy balance. Mass balance is clear to everyone. This is clear to everyone. You all have done reaction. I am not going to go in detail. Correct? This is the temperature reaction. So in this case, instead of this T2, I should have used this T. That's what you are saying. Is that the question? Instead of this T2, I should have used this T. Is that the question? Yes. That is the question. You have pointed. Correct. I will point. Okay. Now let's look at the energy balance. If I wanted to make an energy balance, in this case, whatever the energy of the product is there, whatever the energy of the reactant is there, whatever the energy generated by the reaction, and whatever the energy taken out by the coolant, I have to balance all. Isn't it? So in this case, the energy with respect to the unreacted reactant will be given by what? 1 minus XA into delta H reactant. So delta H reactant is nothing but what? Enthalpy of the reactant. Enthalpy of the reactant, if I am multiplying by 1 minus XA, that gives me the enthalpy with respect to the unreacted reactant present inside the reactant. Correct? Again, delta H product is the enthalpy of the product. And how much product we have formed? XA multiplied by this, isn't it? In addition to these two terms, there is a reaction occurring which is A gives R, which is exothermic, isn't it? So heat of reaction comes into the picture. So heat of reaction is given as delta HR1 XA, and the heat is continuously taken out from the jacket by using this coolant. So that is taken as Q, isn't it? So if I put everything, that should be equal to 0, and if I take a reference temperature of Q. Okay, so this entire term should be equal to 0. This entire term should be equal to 0. If I put all these individual terms in terms of sensible heat, this delta H reactant will be given by Cp dash T2 minus T1, where Cp dash is the specific heat of the reactant. Similarly, in this case, this delta H product I can represent as Cp double dash T2 minus T1, where Cp double dash is nothing but the specific heat of the product, isn't it? And this delta HR1 is nothing but the heat of reaction at temperature T1, isn't it? The actual temperature coming out from the reactor is T2, isn't it? So this delta HR1 is the heat of reaction at temperature T1. Now if I rearrange everything here and represent the equation in terms of XA, what I am going to get? I am going to get Cp dash delta T minus Q divided by minus Cp double dash minus Cp dash delta T minus delta HR1. So this is the equation I am expected to get. Remember I said that this delta HR1 is the heat of reaction at temperature T1, but if I include this particular factor in this, then this becomes the heat of reaction at temperature T2. So this denominator represents the heat of reaction at temperature T2. In fact, this derivation is also done. I am not sure whether you have done it. Okay. Now what this XA is? This XA and this XA, both XA are same. They are same. This XA I have obtained by using mass balance, and this XA I have obtained by using energy balance. Isn't it? And both XA should correspond to the same. Isn't it? But now look at this equation. XA is given as Cp dash delta T minus Q divided by delta HR. What type of nature of the curve I am going to get if I plot XA versus T? I'm going to get more or less a linear curve. It's slightly curved. Why I'm getting slightly curved? Because this CP dash is not constant, it's also a weak function of it. So you get a slight curve instead of getting a straight line, but more or less straight. Isn't it? Here you are getting a sigmoidal curve, here you are getting a straight line. And both these equations will satisfy each other. Isn't it? So this is nothing but what? This is nothing but the heat generated by mass balance, and this is nothing but what? Heat taken out by the coolant. Isn't it? Now the amount of heat generated will be proportional to this XA, and the amount of heat taken out will be again proportional to this XA. Isn't it? And that is what we have plotted here. You can see the amount of heat generated by material balance is given by a sigmoidal curve, whereas the amount of heat taken by the energy balance is represented by more or less a straight line, and both these curves should satisfy each other. So you can see that the points in which these two lines are intersecting, so this point, and this point, these 3 points are the actual operating points, because only at these 3 points your material balance and energy balance is satisfying. So clearly in this case, these are the 3 operating points. These are the 3 operating points for your continuous turbine reactor. Now look at the difficulty with respect to each of these operating points. Okay. Let's say if I operate my reactor here, somewhere here. If I operate my reactor somewhere here. Now at this particular operating point my temperature is low. T1 is slightly low here in this case. So when the temperature is low, the yield of your product is going to be low. Isn't it? Remember, the rate of reaction increases with temperature. In this case, temperature is lower. You are operating your reactor at a lower temperature. So yield of your product is going to be low if you are operating at this temperature. So you may not be interested because your profitability is not there. Now let's look at another operating point here. This particular point, the temperature is T3. Definitely T3 is sufficiently high. T3 is sufficiently high. Rate of reaction is also very high here. There is no problem with respect to yield. The problem is at such a high temperature your catalyst may get deactivated. Your catalyst may get deactivated. Your product may get degraded. Isn't it? If you are operating with such a high temperature. So clearly this particular operating point is also not suitable. Not suitable. The only operating point you are left with is this operating point. Now at this operating point there is another problem. You can see that in this operating point, let's say there is a small deviation. There is a small deviation in your operating variables. Small disturbance came into the system, and because of that disturbance, let's say this temperature T2 is slightly increased to T2 dash. What will happen? If this temperature T2 is increased slightly to T2 dash, you can see that the amount of heat generated by mass balance is higher than the amount of heat taken out by the coolant. So if the amount of heat generated by the mass balance is more than the amount of heat taken by the coolant, what will happen to the temperature of the reactor? It will increase. So eventually you will move from this point to this point. If there is a small disturbance, you will move from this point to this point if the temperature T2 is higher. Let's say temperature T2 is slightly lower than this value. What will happen? Let's say somewhere here. So amount of heat generated by mass balance is lower than the amount of heat taken by the coolant. So eventually you will reach from this point to over. Now you can see that even though I am left with operating at this operating point O2, but this operating point O2 is unstable operating point. If there is a small disturbance in the temperature, you will either move to O3 or O1. Okay? Unstable operating. But you have no choice but to operate here. Why? Because if you operate here, then your yield is low. If you operate here, then the catalyst is getting deactivated. Isn't it? So in this case, definitely you need to add external intervention to make the system stable. Isn't it? Correct? Is it clear? Everyone? Is it clear? System is clear? Okay, now look at what will happen at this point. Let's say here, let's say some small disturbance is there. Because of that, if T1 increases to some slightly higher value, you will see that somewhere here the amount of heat generated will be lower than the amount of it taken by the coolant, so eventually we will come back to this. Similarly at this point, so both O1 and O3 are the stable operating points. But O2 is a unstable operating point. That is what is shown in the next graph. You can see at O3 if there is a disturbance, this disturbance is going to die. At T1 if there is a disturbance, at O1 if there is a disturbance in T1, this disturbance is going to die. But if there is a disturbance at T2, if T2 is increased slightly, it will reach to T3. If this T2 is decreasing slightly, then it will reach to T1. So this is the unstable. You can make it stabilize. You can stabilize this process by performing the external intervention. How? You can apply the external loop, control loop, and that will make sure that the temperature inside the reactor remains exactly at T. Okay? Is it clear? The requirement is clear to everyone. क्या हो गया यार एकदम ऐसा मतलब why I usually see that people are not interested, why there is this this disinterested type of, just by looking at you I can make out whether you are interested in the class or not interested in the class. Please participate in the class and you can ask your seniors. Okay. I usually like people where they are interacting, they are asking questions. Class is live. Otherwise, I have done this 4-7 times. It's not good for me. I am not going to get anything. And there is no incentive for good teaching in the institute. I tell you. Okay. There is no incentive. So unless you do something from your side, I am not going to get any motivation. So I am requesting all of you to keep me motivated. Okay.
So, what if T2 is still high for very low concentration?
If T2 is
Still high, like you say from a T3, this is very high temperature. And what if T2 is similar?
if you wanted to operate that also is possible. Let's say, okay, I understand your question. Let's say if you wanted to operate somewhere here, is that what you are doing? You can do that. In fact, you can operate here somewhere here also. Why? Whenever there is a higher amount of heat is generated, that higher amount of heat is taken out with the both coolant. So remember, coolant will be increased in that case. So you are going to apply the external intervention that will increase the amount of coolant action. There is no problem. Okay. So two cases we have done. Remember, the first case was suppressing the effect of external disturbance on the system, and the second case was to make inherently unstable process stable. Okay, and the last case is to optimize the process. Okay, so this is the example in which you can see that there is a series reaction taking place, A gives R and R gives S. Here the desired product is R and undesired product is S. Isn't it? The reaction is endothermic, so you need to supply the heat. How you are supplying the heat? The steam is flowing through the jacket, and the heat dissipated by the steam is used for heating the reaction mixture inside the reactor. Now, in this particular case, your desired product is R and undesired product is S. Okay. What should be the strategy to optimize this? And why optimization is at all required? Do you see there is a need of optimization here? And why it should be optimized? Why can't I put one starting steady state value and I don't change anything? Let's just keep for it. I don't want to maintain something. Is there anything going to happen? So let's say I maintain the higher steam flow rate, so temperature will be higher. Because of that, what will happen? The rate of this first reaction will be higher. So A will be converted to R faster, but then eventually R will also get converted to S. So if you use the higher value of steam flow rate, then the reaction is going to be fast, but then at the same time the higher amount of S will be formed. Let's say if I keep this steam flow rate lower value, then R will be formed with a lower rate and the entire reaction will take longer time to complete. Isn't it? Correct? And ultimately in this case the cost is arising from what? Cost is arising from the, so see there is a cost of reactant, then there is a cost of saving the R, and also the cost is associated with how much steam is getting used. So I wanted to minimize the amount of steam used and I wanted to maximize the profit I can make from the. So in this case, the profit can be represented as revenue from the sales of R minus cost of reactant A, and then the steam flow rate. Instead of maintaining the constant steam flow rate, I am going to change the steam flow rate depending on how much steam flow rate I require time to time. Remember in this case, initially when I am having all A present inside the reactor, I need to have the faster reaction rate. Why? Because A will be converted faster to R. But once the sufficient amount of R is formed, then I want to suppress the reaction. So I wanted to reduce the steam flow rate after that. So instead of having the constant steam flow rate, I should have a higher steam flow rate initially, and that steam flow rate should decrease as I produce sufficient amount of R in order to suppress the formation of S. Do you all agree? Isn't it? So clearly the steam flow rate, instead of maintaining a constant value, I should get the trajectory of the steam flow rate. Trajectory of the steam flow rate is going to vary with respect to time, and that is why this integration is coming in here. So 0 to TB is the batch time, and I am integrating the steam flow rate over the time and multiplying it by a cost factor. So this is giving me the cost associated with the cumulative amount of steam I am going to use throughout the batch time. Correct? Isn't it? And this particular objective function I wanted to maximize. Isn't it? So I wanted to find out the optimum value of FSC by solving this optimization problem. And once I get the optimum value of FST, the objective of the control problem is to maintain this optimum value of the FST inside the reactor. So there are two parts in this particular problem. One is the optimization of the process. Once I optimize the process, whatever the optimal trajectory of FST I am going to get, that optimal steam flow rate trajectory I need to maintain inside the reactor. There are two parts. There is one optimization and then there is the control. And this problem is typically referred as optimizing control or optimal control. Okay, you can do this online also. In that case, people call it as an online optimal control. Alright. We will see the tutorial 1 which is based on this. So tutorial 1 will be on Monday. In tutorial 1 we will see one such example. Okay, alright. So in this case you can see that this FST will be initially maintained to a higher value and it will be decreasing as we move along the time, isn't it? Because that is what is going to give you the higher amount of R and lower amount of steam. Isn't it? Alright. So this is the last requirement for which the control is required, and we will look at the why model required in process control and other details in the next class. Before we conclude the class today, we will have only 2 tutorials on Monday and Friday. If you have any classes on Monday, remember the timing is 2 to 3, not 1 to 2. Timing is 2 to 3. Tutorial time is 2 to 3. Please attend all the tutorials. You will understand this course better if you attend all the tutorials. There are around 14 tutorials and we do all the tutorials. So please attend all the tutorials. Okay. And if you are thinking that this course is open book, everything is open, you will be able to do it. Take my word, you will not be able to do it. Okay. Typically, I have seen that in this course, those people don't study because they feel that the course is open book. You will not find anything in the book. Everything will be outside of the book. No question from the previous minor, major will appear. No question from the book will appear. All the questions will be new. Giving it open because I don't want you to memorize the content. I don't want you to memorize the content. I want you to understand the content, not memorize. That is why it is open. Okay, alright. So we stop here unless you have any question.